Now it's recording. Why single function doesn't exist? Carl, do you know?
There's a discontinuity
Where?
at the point where it jumps from 0 to 1.
From 0 to 1?
I mean, at the edges.
No.
Oh, it doesn't come never to 0, right? Yeah, I got it now.
Yeah. At point 0, this function is not defined. Because at point 0, we have sine 0 divided by 0. 0 divided by 0 is? In the morning, we had the math class. How many of you were in the math class?
Not a number.
It's not a number. It's N-A-N. It's none. It's not a number. However, we know the limit of x goes to 0 of sine x over x. If we use the Hopital rule, the result will become 1. In other words, from right and left, if we approach, we get to 1. But at point 0, it does not exist. We cannot have 0 divided by 0. And simply because of that, we cannot produce such a signal. Because if it existed, then we never had an energy problem, because the energy would be infinity in there. This is how it's related to the energy. But because of only one single point, this does not exist. However, in the world of digital, you sit by the computer, you write sine x divided by x. If x is not equal to 0, you write your code, everything is okay. Otherwise, just put 1 and then do the whole thing. So in the world of digital, we can write it down and we can produce it. In other words, I can use this kernel, which is pretty cool, in my interpolation. Why it is pretty cool? Because so quickly these rings go to the values which I can neglect it. Okay? So quickly it will go to the values that I can neglect it. Now, when we come to using, and I'm assuming that you were still thinking about the question that I asked 10 minutes ago. Now, we have this picture. We have this picture. And I am using different methods to enlarge it. When I use the nearest neighbor, as you remember, I said that if you are just considering this part, it's perfect. It's perfect. But when it comes to these directional lines, we are doomed, right? This zigzag effect. Don't talk about that. So let's pass. We come to the bilinear, bicubic, SV-line, and sync. And then when I look at them, I also understand that bilinear is not very sharp, because actually if you look closer enough, you will be able to see that you have 3 tones here, whereas in these regions you have more continuous changes of tone. Now I am coming to sync. Do you see the sync? And do you see that we have lots of lines? Why do we have these lines?
Because of the negative values?
I don't know, you tell me.
I just did.
No, you ask question.
Because of the negative values.
Because of the negative values, what do I have?
This kind of ripple effect.
It's a ripple effect. And because of negative value, I have the dark parts. And because of the positive value in the other side, I have these broad lines. So these wings, these ripples, is causing something which is called the ring effect. And this is not desirable. This is not good. We do not like it. Okay? So we answer to the questions. And that is get back to the Nyquist theorem, which I already discussed about the aliasing. And what in the pictures, the first picture you see is that if you want to do the sampling, we have to look at what is the frequency of my signal. If the blue line is the curve that I want to sample, if I want to take a sample of that one, if I do not get enough number of samples, I may end up with a green line. If I have only one sample, it will be a line. And if I have more number of samples, I can start to actually reconstruct what I wanted to have. And we know that the frequency of the sampling should be more than twice of the maximum frequency. Now, the example that I gave with the address, here we can see that what will happen if I have the aliasing problem. You can see this ringing effect. This is not desirable. This is not good. So what we do, usually with the texture, with the pattern, which looks like this type of patterns, we have these aliasing problems. Here you can see that we have the aliasing problems in here. Now, there is a way, luckily, that we can get rid of these aliasing problem. And this aliasing problem can be solved by something which we will talk about it. You will have a homework about it in this course called low pass filter, LPF. We will talk about this low pass filter later. If we are using a low pass filter on the image before we do the sampling, we can actually start to kill so many of the high frequencies. So the camera that I have, the number of the sampling rate that it has will satisfy the Nyquist condition that I wanted to have. So if I am applying the low pass filter, you can see cool image without having any aliasing problem. Again, aliasing is something which is not, we don't desire to see it because it makes our eyes to feel tired. Cool. So what we talked today was, we talked about sampling, quantization. I'm assuming that you are expert of sampling and quantization. We will get back to the concept of quantization maybe in 1 month when we are talking about compression, because this is something which is very lossy. We talk about zooming, and by zooming I mean the upsampling, I mean super resolution, I mean a spatial resolution is to increase the spatial resolution. And we said that in order to do that, the strong tool and the kind of conventional tool is interpolation. And then we talk about different type of interpolations. Now, the next topic that we will talk is image enhancement. What does the word enhancement means?
Better.
Make the quality better. We want to make the image quality better. So in order to enhance an image, there are several forms, because it depends how we are looking at the image, from which aspect we consider an image to be a good image or bad image. And we will start by talking about illumination enhancement. In other words, we have some dark image or bright image, we try to enhance that one. Then we will talk a little bit about the noisy images. We try to see how we can get rid of these noises and so on. Okay? Now, do you have any question? Well, if you have no question, then I think here we are. That's all I wanted to say. And have a nice time. I put the notes into the module.